Hi, Michael.
Hey, Charles, how's it going?
It is going quite well. Thank you very much for asking. How are things going with you?
I can't complain because I've been barred by a judge.
I'm pretty sure you can still complain. Complaining is a fine art that requires lots of practice. Guess what we're going to do today?
I'm reading Decision Making and Reinforcement Learning, which is very exciting.
It is.
Except the hyphen. Yeah.
Except for the hyphen?
Yeah, the hyphen's wrong.
Why?
Because it's not decision dash making.
You're right. I normally don't do that, but people always want to put a dash. So what I'm going to do is for you, Michael, just for you, I'm going to remove the dash.
Thank you.
And I'm going to put it over here where it belongs.
No.
No. There. Well, Michael, this is the first of our discussions on the last mini course of machine learning, reinforcement learning, which I believe you know a little bit about.
I am very interested in reinforcement learning.
Excellent. So I'm just going to do a little bit of background. It's going to be relatively short and straightforward. We're going to do a couple of quizzes because I know how much you like quizzes. And then we're just going to go back and forth and see what we get to learn about reinforcement learning. Sound good?
Excellent.
Excellent. Okay, so let's get started. Okay, Michael, so before we get started diving into a particular formalism or framework that I want to talk about that we're going to use for most of this mini course, or at least the first half or so of it, I want to remind everybody what the differences are between the three types of learning that we said we were going to look at over this entire course. Do you recall what they are?
Well, reading them off the slide, supervised, unsupervised, and reinforcement.
That's right. And, you know, again, these things are all strongly related to one another, but it's very useful to think about them as being very separate. So just as a reminder, supervised learning sort of takes the form of function approximation, where you're given a bunch of XY pairs, and your goal is to find the function f that will map some new x to a proper y. You recall that?
Yep.
Unsupervised learning is very similar to supervised learning, except that it turns out that you're given a bunch of x's, and your goal is to find some f that gives you a compact description of the set of x's that you've seen. So we call this clustering or description as opposed to function approximation. And finally, we're getting to reinforcement learning. Now, reinforcement learning is actually a name that means many things in different fields, and here we tend to talk about it in a relatively specific way. And superficially, it looks a lot like supervised learning, in that we're going to be given a string of pairs of data, and we're going to try to learn some function. But in the function approximation case, the supervised learning case, we were given a bunch of x and y pairs. We were asked to learn f. But in reinforcement learning, we're going to be given something totally different. We are instead going to be given x's and z's, and I'll tell you what the x's and the z's stand for in a minute, and then we're going to have to learn some f that is going to generate y's. And so even though it's going to look a lot like function approximation, it's going to turn out that it's going to have a very different character. And that's really what the next few slides and a little bit of discussion is really about, is understanding what that character is. You'll also notice from the title here that I have decision-making and reinforcement learning, and that's because reinforcement learning is one mechanism for doing decision-making. And again, I'll define that in just a second. Okay, so you with me, Michael?
I think so. So should y be circled? Because in some sense, you underlined the things we were given and you circled the things we needed to find. So y is something that we're going to find, right?
Yeah, I suppose so. I like that.
All right, interesting.
Now it's a theta.
It's a y trapped inside of a theta.
Ugh.
And it's yelling, why?
I like that. I'm a y trapped in a theta. I could write a book about that. Okay, good. That's a good point, Michael. So before we were effectively trying to learn one thing, and here we're still learning one thing because it's going to produce another thing sort of deterministically, usually. But it's worth pointing out that we are going to be figuring out how to produce both of these things as opposed to being given those things. Good job. Okay, so you ready to move forward, Michael, with an example and a quiz?
Awesome.
Excellent. Michael, here is a world. In fact, for the purposes of this discussion, it is the world. Okay, so imagine the entire universe is well described by this picture over here. Okay? Now, this is called a grid world, which is something that people in reinforcement learning love to think about because it's a nice approximation for all the complexity of the entire universe. Now, this particular world is a 3x4 grid. So you have, 1, 1, 2, 1, 3, 1, 4, 1. You have 1, 2, 1, 3, and so on and so forth. For the purposes of this discussion, we can think of the world as being a kind of game where you start out in a state, which we're going to call the start state, and you're able to execute actions, one of these four, up, down, left, or right, And the purpose is to wander around this world in such a way that eventually you make it to this goal over here, this little green spot. You see that, Michael?
Yep.
And under all circumstances, you must avoid the red spot.
No.
Exactly. Now, for this particular example, up does what you think it does, down does what you think it does, as do left and right. But if you find yourself at a boundary, such as right up here in this upper left-hand corner, and you try to go up, you just stay where you are. If you try to go left, you just stay where you are. But if you go right, you do actually end up in the next square. Got it?
I think so.
Okay. 3 last things. 1, this little black space here is a place you can't enter into. So it acts just like a wall. This green space is the goal. And once you're there, it's over. The world is over and you get to start over again. And once you enter into the red spot, the world is also over and you have to start over again. So you can't go through the red square to get to the green square. Okay, you got it?
Yeah.
Excellent. So here's the quiz. Given this particular world with the physics I just described to you, and given these actions that you can take, up, down, left, and right, what is the shortest sequence of actions that would get us from the start state to the goal state? And you can just type in the words up, down, left, and right, separated by spaces or commas or anything like that. Okay? Say semicolons are allowed, colons are not.
Yeah, good.
I'm
glad you made that distinction.
Well, it's an important one to make. Okay, you got it?
Yeah, I think so.
All right, cool. So let's see what you get then. Go. Okay, Michael, you got an answer for me? This isn't meant to be a hard quiz.
Oh, good. Because I actually have 2 answers for you.
Oh, I like that.
So I would say right, right, up, right.
Okay, so right, right, up, right.
But I feel like I could have also said up, right, right.
And you could have. Both of those are acceptable. Right, right does what you think it does. You move right, and then up, and then up, and then right. And that takes 5 steps. Or you could have gone up, right, right, which would also take you 5 steps. So that's pretty easy, right?
Yeah, I thought so.
Right. So yes, either of these would be correct. We're going to stick with this one in particular since they're equal, so we got to pick one of them. Though this does point out something that often in a decision problem like this, there are in fact multiple answers or multiple optima. If I can tie it back to our randomized optimization discussions. Okay, so you got the quiz, you got the world, you understand what you can do here. Yes?
Yep.
Okay, cool. Now I'm going to throw in a little wrinkle. I'm going to change the world just a little bit, Michael. Okay, that last one was really easy, and it was easy for a bunch of reasons. But one of the reasons it was easy is that every time you took an action, it did exactly what you expected it to do. Now I want to introduce a little bit of uncertainty or stochasticity into the world. So let me tell you exactly what that means. When you execute an action, it executes correctly with probability of 0.8. So 80% of the time, if you go up, it goes up, assuming you can go up. If you say down, it goes down, assuming you can. Left, it goes left. Right, it goes right. Got it?
Yeah.
Now, 20% of the time, the action you take actually causes you to move at a right angle. Now, of course, there are 2 different right angles you could go to. If you go up, you could go either left or right at a right angle. And so that 20% gets distributed uniformly. Okay? Does that make sense?
Yeah, I think so. And so if you're in the start state and you try to go up, then there's a 10% chance that you would attempt to bump into the wall?
Yes.
And then you just stay where you are, I guess.
Right. So if you decide to execute the up action here, you have a 80% chance of moving up. You have a 10% chance of moving to the right. And you have a 10% chance of moving to the left, but of course you would bump a wall and you would end up right back where you started. Got it?
Yeah.
Okay, good. So here is my quiz question for you, Michael. As you recall, we came up with 2 sequences, and the one that I decided to keep was up, right, right. My question to you is, what is the reliability of the sequence up, right actually getting you from the start to the goal given these probabilities, this uncertainty?
And so we're just going to try that sequence and ask whether or not it actually got us to the goal.
Exactly. And when I say reliability, I really mean what's the probability of it actually succeeding.
Interesting. Okay.
All right. So let's see if we can figure out the answer. You ready?
I'm ready.
All right. Go. Okay, Michael, do you have an answer?
I have an answer indeed.
Okay, what's the answer?
Okay, maybe I don't have an answer indeed, but I have the ability to compute one.
Okay.
I'm doing some math.
So why don't you walk me through the math you're doing?
I got 0.32776.
That is correct, Michael.
Woohoo! That was trickier than I thought.
Okay, well, show me what you did.
All right. So the first thing I did is I said, okay, well, this is not so hard because from the start state, if I execute up, up, right, 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 each of those things works the way it's supposed to do independently with probability 0.8.
Yep.
And so 0.8 raised to the 5th power gives me the probability that that entire sequence will work as intended.
Exactly. And what is 0.8 to the 5th? Do you know?
32,768 with a decimal point in front of it because, powers are 2.
Wow. That is correct. But I noticed that 32768 is not 32776.
No, they differ by a little smidge.
Mm-hmm.
So this is what occurred to me next, is there any way that you could have ended up falling into the goal from that sequence of commands, not following the intended path? So since actions can have unintended consequences, as they often do, I was going to ask, okay, so if I go up in the first step, there's a probability 0.1 that I'll actually go to the right.
Yep.
From there, if I go up, there's a 10% probability that I'll actually go to the right.
Mm-hmm.
From there, the next thing I do is take the right action, but that can actually go up with some probability, 0.1.
Yep.
And then another 0.1 to get to, for the next right action to actually cause an up to happen.
Mm-hmm.
And then finally, that last right might actually execute correctly and bring me into the goal. So I could go underneath the barrier instead of around the barrier with that same sequence. It just isn't very likely.
Okay, well, how unlikely is it?
All right, so I did 0.1 times 0.1 times 0.1 times 0.1 times 0.8.
So the 0.1 to the 4 times 0.8, and that's right. So this is the probability that the four of these go wrong. In fact, exactly the first 4 go wrong, and the last one goes right.
Right.
And that's equal to some very, very small number, and when you add it up, you end up with 0.32776. So in fact, that's equal to 0.00008. And that's how you get that number, and that's correct. And you'll notice that this sequence happens to work out to be the second sequence that we had option for.
Yeah, the other thing that took us to the goal, was
Right.
exactly the probability of executing that action, executing that sequence of transitions given the first command.
Yeah, and I think it would work the other way too. No, it wouldn't quite work the other way. If you had done the sequence right, what is it? Right, up, right.
Yeah.
In order for that one to work out, it had 0.8 to the 5 of working. And for it to work out wrong but work out right, the right would have to send you up, and then the ups would have to send you right. And so it would actually work out to be the same.
Yeah.
So no matter which of the two sequences you came up with, they would have the same probability of succeeding.
Neat.
Nice. That's actually kind of cool. So good job, Michael. Very good job on the quiz. A lot of people forget this part. And in fact, if you forgot that part and got just this part right, we actually let you pass. But it was wrong.
I was kind of expecting you to get it wrong, but I'm glad you got it right too.
Thank you, Michael. I appreciate your faith in me. I wrote the quiz. Actually, I stole this from a book, whose little words are now showing up in front of you exactly where you can go through the details of this quiz. Okay. All right, Michael. So you might ask yourself why I brought this up. And the reason I brought this up is because what we did in the first case where we just came up with the sequence up, right, is we sort of planned out what we would do in a world where nothing could go wrong. But once we introduce this notion of uncertainty, this randomness, this stochasticity, we have to do something other than work out in advance what the right answer is and then just go. We have to do something a little bit more complicated. Either we have to try to execute these and then every once in a while see if we've drifted away and then replan, come up with a new sequence wherever it is we happen to end up, or we have to come up with some way to incorporate all of these uncertainties and probabilities so that we never really have to rethink what to do in case something goes wrong. So what I'm going to do next is I'm going to introduce a framework that's very common that people use as a way of capturing this stuff, capturing these uncertainties directly. Okay? You ready?
Yeah.
Excellent. So this is the framework that we're going to be using through most of the discussions that we'll be having, at least on reinforcement learning, at least single agent reinforcement learning. And it's called the Markov decision process. This should sound familiar to you, Michael.
Well, you did say we were going to talk about decisions.
That's true. And we need a process for making decisions. And we're going to introduce something called the Markovian property as a part of this discussion. And I'll tell you exactly what that means in a moment. So I'm just going to write out this framework and tell you what it is and what the problem it produces for us, and then we're going to start talking about solutions through the rest of the discussion. So a Markov decision process tries to capture worlds like this one by dividing up in the following way. We say that there are states, and states are a set of tokens that somehow represent every state, for lack of a better word, that one could be in. So does that make sense to you, Michael?
Yeah, I think so.
Okay, so what would the states be in the world that we've been playing around in so far?
So the only thing that differs from moment to moment is where I guess I am, like which grid position I'm in. So I feel like each different grid position I could be in is a state. Maybe there's a state for being successfully done or unsuccessfully done.
That's possible, but let's stick with the simple one. I like that one because that's really, I think, easy to grasp. So there are at least, of all the states one could reach, there's 4 times 3 minus 1 since you can never reach this state. Although we could say it is a state, we just happen to never reach it. So at most, if we just think of this grid literally as a grid, there are something like 12 different states. And we can represent these states as their XY coordinates, say. We could call this the start state as, say, 1, 1, which is sort of how I described it earlier. We could describe the goal state as 4, 4, and say this is how we describe our states. Or frankly, it doesn't matter. We could call these states 1, 2, 3, up to 12. Or we could name them Fred and Marcus. It doesn't really matter. The point is that they're states, they represent something, and we have some way of knowing which state we happen to be in. Okay?
Sure.
Okay. All right, so we got states. So next is what's called the model or the transition model. Sometimes people refer to it as a transition function. And basically, it is a function of 3 variables. It's a state, an action, which I haven't defined for you yet, and another state. In fact, since I haven't defined what an action is for you yet, let's skip that and actually do define actions for you. So the third part of our model are actions. Actions are the things that you can do in a particular state. So what would the actions be in this world?
Well, the 4 different decisions I could make were the up, down, left, and right. Though it's maybe a little confusing because I think those were also the 4 possible outcomes.
That's true. Well, no, there were other outcomes. You could stay where you were. Right. So these are actually the actions. These are the things that when I'm in a given state, I'm allowed to execute. I can either go up, go down, go left, or go right. You'll notice that, as I described before, there was no option not to move. But there could have been, and there could have been other actions like teleport, or there's anything that you can imagine. But the point is that your action set represents all of the things that the agent, the robot, the person, or whatever it is you're trying to model is allowed to do. Now, in its full generalized form, we tend to think of the set of actions that one can take as being a function of state, because there are some states you can do some things, and some states you can't do those things. But most of the time, people just treat it as a set of actions, and the actions that aren't allowable in a particular state simply have no effect. All right, so we understand states. They're the things that describe the world. We understand actions. Those are the things that you can do, the commands you can execute when you're in particular states. And what a model describes, what the transition model describes, is in some sense the rules of the game that you're playing. It's the physics of the world. So it's a function of three variables: a state, an action, and another state, which, by the way, could actually be the same state. And what this function produces is the probability that you will end up transitioning to state S prime, given that you were in state S and you took action A. Got it?
I think so. So the S prime is where you end up, and the SA is what you're given. So you plug these 3 in. Oh, I see, and you get a probability out. But the probabilities have to add up to 1 if you sum it up over all the S primes.
Right. That's exactly right. So, for example, if you think about the deterministic case where there was no noise, then this is a very simple model. If I'm in the state, the start state, and I take the action up, then what's the probability I end up in the state immediately above it?
Was that a 0.8?
No, when we first started in the deterministic world.
Oh, that was probability 1.
Right, and what would be the probability you ended up in the state to the right?
Probability 0.
Right. In fact, the probability that you end up in any of the other states is 0 in the deterministic world. Now, what about the case when we were in the non-deterministic world where an action would actually execute faithfully only 80% of the time? If I'm in the start state and I go up, what's the probability that I end up in the state above?
That was 0.8.
Right. What's the probability I end up in the state to the right?
That was 0.1.
And what's the probability I end up where I started?
That was also 0.1.
Right, and 0 everywhere else. And that's just sort of the way that it works. So the model really is an important thing. And the reason it's important is it really does describe the rules of the game. It tells you what will happen if you do something in a particular place. It captures everything that you know about the transition of the world, what you know about the rules. Got it?
Did you call it physics before?
I called it the physics of the world.
Huh.
These are the rules that don't change.
But they're very different from real-world physics.
Well, yeah, although they don't have to be. I mean, in some sense, you could argue that a Markov decision process, what we've described so far, these three things, in fact, do describe the universe. The states are, the positions of all the atoms, the positions and velocities of all the atoms in the universe. The transition models, as you do take certain actions in the world, whatever they are, how the state of the universe changes in response to that. And the actions are whatever those set of actions can be.
And it can be probabilistic or it's not probabilistic?
It can definitely be probabilistic. Transition models are, by their very definition, probabilistic.
Gotcha.
Now, I actually snuck something important in here. I actually stuck two things that are important in here. The first is what's called the Markovian property. Do you remember what the Markovian property is, Michael?
From what?
From, I don't know. Actually, where does the Markovian property come from?
I'm going to say Russia.
Okay, yeah, from the Russian.
Yeah, so I have Russian ancestors, and they passed on to me this idea that Markov means that you don't have to condition on anything past the most recent state.
That's exactly right. The Markovian property is that only the present matters.
And they had to pass that down to me, one generation at a time because, Markov property.
That's exactly right. That was very good, Michael. So what does this mean? What this means is our transition function, which tells you the probability you end up in some state S prime, given that you were in state S and took action A, only depends upon the current state S. If it also depended upon where you were 20 minutes before then, you would have to have more S's here, and then you would be violating the Markovian property.
So is this do historians hate this?
Well, one never learns anything from history.
No, you're supposed to learn from history or you're doomed to, I don't know, let me make something up. Repeat it.
Fair enough. Historians probably don't like this, but there is a way for mathematicians to convince them that they're okay with it. And the way that mathematicians convince you that you're okay with this is to point out that you can turn almost anything into a Markovian process by simply making certain that your current state remembers everything you need to remember from the past.
I see.
So in general, even if something isn't really Markovian, you need to know not only what you're doing now, but what you were doing 5 minutes ago. You could just turn your current state into what you're doing now and what you were doing 5 minutes ago. The obvious problem with that, of course, is that if you have to remember everything from the beginning of time, you're only going to see every state once, and it's going to be very difficult to learn anything. But that Markovian property turns out to be important, and it actually allows us to solve these problems in a tractable way. But I snuck in something else, Michael. What I snuck in is this idea about the transition model is that nothing ever changes. So the second property that matters for Markov decision processes, at least for the sets of things that we're going to be talking about in the beginning, is that things are stationary. That is, for the purposes of this discussion, it means that these rules don't change over time. That's one notion of stationary. Okay?
Does that mean that the agent can never leave the start state?
No, the agent can leave the start state anytime it takes the action that gets it out of the start state.
How is it stationary then?
It's not stationary. The world is stationary. The transition model is stationary. The physics are stationary. The rules don't change on you.
The rules don't change.
Right.
Okay, I see.
There's another notion of stationary that we'll see a little bit later. Okay, last thing to point out about the definition of a Markov decision process is the notion of reward. So reward is simply a scalar value that you get for being in a state. So for example, we might say, this green goal is a really good goal. And so if you get there, we're going to give you $1. This red goal, on the other hand, is a very, very bad state. We don't want you to end there. And so if you end up there, we're going to take away $1 from you.
What if I don't have $1?
Someone will give you the $1. The universe will give you the $1. Or
and then take it away.
The universe will take it away. Even if you don't have it. You'll have negative dollars.
Oh, man.
Okay, so reward is very important here in a couple of ways. Reward is one of the things that, as I'm always harping on, encompasses our domain knowledge. So the reward you get for an estate tells you the usefulness of entering into that state. Now, I wrote out 3 different definitions of R here because sometimes it's very useful to think about them differently. I've been talking about the reward you get for entering into the state, but there's also a notion of reward that you get for entering into a state and taking an action. There's a reward or being in a state and taking an action. There's a reward that you could get for being in a state, taking an action, and then ending up in another state as prime. It turns out these are all mathematically equivalent, but often it's easier to think about one form or the other. But for the purposes of the, for the rest of this discussion, really you can just focus on this one, the reward or the value of entering into a state. And those 4 things by themselves, along with this Markov property and non-stationarity, defines what's called a Markov decision process or an MDP. Got it?
I'm a little stuck on how those could be mathematically equivalent.
Well, we'll get to that later. Do you like a little bit of intuition?
Sure.
Well, you can imagine that just as before we were dealing with the notion of making a non-Markovian thing Markovian by putting a little bit of history into your state, you can always fold in the action that you took to be in a state or the action that you took to get to a state as a part of your state.
But that would be a different Markov decision process.
It would, but they would work out to have the same solution.
Oh, I see.
Speaking of solutions, this is the last little bit of thing that you need to know, and that is this defines a problem. But what we also want to have whenever we have a problem is a solution. So the solution to a Markov decision process is something called a policy. And what a policy does is it's a function that takes in a state and returns an action. In other words, for any given state that you're in, it tells you the action that you should take.
Like as a hint?
No, it just tells you this is the, I suppose you don't have to do it, but the way we think about Markov decision processes, that this is the action that will be taken.
I see. So it's more of an order.
Yes, it's a command.
Okay.
So that's all a policy is. A policy is a solution to a Markov decision process. And there's a special policy, which I'm writing here as policy star, or the optimal policy. And that is the policy that maximizes your long-term expected reward. So of all the policies you could take, of all the decisions you might take, this is the policy that optimizes the amount of reward that you're going to receive or expect to receive over your lifetime.
So like at the end?
Well, yeah, at the end. Or at any given point in time, how much reward you're receiving. From the Markov decision process point of view, there doesn't have to be an end.
Okay. Though in this example, you don't get anything, and then at the end, you get paid off.
Right. Or unpaid off.
Right.
If you fall into the red square. So actually, your question points out something very important here. I mentioned earlier when I talked about the 3 kinds of learning that the supervised learning and reinforcement learning were sort of similar, except that instead of getting Y's and X's, we were given Y's and X's and Z's. And this is exactly what's happening here. Here, what we would like to have if we wanted to learn a policy is a bunch of SA pairs as training examples. Well, here's the state and the action you should have taken. Here's another state and the action you should have taken, so on and so forth. And then we would learn a function, the policy, that maps states to actions. But what we actually see in the reinforcement learning world, in the Markov decision process world, is we see states, actions, and then the rewards that we received. And so, in fact, this problem of seeing a sequence of states, actions, and rewards is very different from the problem of being told, this is the correct action to take, maximize a function, or find a function that maps from states to action. Instead, we say, well, if you're in the state and you take this action, this is the reward that you would see. And then from that, we need to find the optimal action.
So pi star is being the F from that previous slide?
Right.
And R is being Z?
Yes.
And Y is being A?
And S is being X, or X is being S.
Gotcha.
Right.
So, but I'm a little confused about this notion of a policy. So we have the thing that we tried to do to get to the goal was up, up, right, right, right.
Yes.
I don't see how to capture that as a policy.
It's actually fairly straightforward. What a policy would say is, what state are you in? Tell me what action you should take. So the policy basically is this. When you're in the state the start state, the action you should take is up. And it would have a mapping for every state that you might see, whether it's this state, 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 or even these 2 states, and it would tell you what action you should take. And that's what a policy is. A policy, very simply, is nothing more than a function that tells you what action to take in any state you happen to come across.
Okay, but the question that you asked before was about up, up, right, right, right.
Mm-hmm.
And it seems like because of the stochastic transitions, you might not be in the same state Like you don't know what state you're in when you take those actions.
No. So one of the things for what we're talking about here for the Markov decision process is there are states, there are actions, there are rewards. You always know what state you're in, and you know what reward you receive.
So does that mean you can't do up, right, right, right?
Well, the way it would work in a Markov decision process, so what you're describing is what's often called a plan. It's tell me what sequence of actions I should take from here. What a Markov decision process does and what a policy does is it doesn't tell you what sequence of actions to take from a particular state. It tells you what action to take in a particular state. You will then end up in another state because of the transition model, the transition function. And then when you're in that state, you ask the policy, well, what action should I take now?
Okay.
Right. So this is actually a key point. Although we talked about it in the language of planning, which is very common for people who, for example, taken an AI course, to think about this in terms of planning. What are the things that I can do to accomplish my goals? The Markov decision process way of thinking about it, the reinforcement learning way of thinking about it, or the typical reinforcement learning way of thinking about it, really doesn't talk about plans directly, but instead talks about policies, from which you can infer a plan. But this has the advantage that it tells you what to do everywhere, and it's robust to the underlying stochasticity of the world.
So is it clear that that's all you need to be able to behave well?
Well, it's certainly the case that if you have a policy, and that policy is optimal, it does tell you what to do no matter what situation you're in.
Okay.
And so if you have that, then that's definitely all you need to behave well.
But, I mean, could it be that you want to do something like up, right, 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 which you can't write down as a policy?
Why can't you write that down as a policy?
Because the policies are only telling you what action to do as a function of the state, not like sort of how far along you are in the sequence.
Right, unless, of course, you fold that into your state somehow. But that's exactly right. I mean, the way to think about this is the idea of coming up with a concrete plan of what to do for the next 20 time steps is different from the problem of whatever step I happen to be in, whatever state I happen to be in, what's the next best thing I can do? And just always asking that question. If you always ask that question, that will induce a sequence, but that sequence is actually dependent upon the set of states that you see. Whereas in the other case where we wrote down a particular policy, you'll notice that was only dependent upon the state you started in, and it had to ignore the states that you saw along the way. And the only way to fix that would be to say, well, after I've taken an action, let me look at the state I'm in and see if I should do something differently. But if you're going to do that, then why are you trying to compute the complete set of states? Or the complete set of actions that you might take.
Okay.
Okay, so there you go. Now, a lot of what we're going to be talking about next, Michael, is given that we have MDP, we have this Markov decision process defined like this, how do we go from this problem definition to finding a good policy? And in particular, finding the optimal policy.
That makes sense.
Good. And there you go. Okay, so I want to talk about two things on this little slide here. The first one is kind of a general observation about rewards and what makes the reinforcement learning MDP problem different from the supervised learning problems that we did before. And that's this notion of not just rewards, but this notion of delayed rewards. So what do I mean by that? Well, so if you think about the way we've set up this kind of problem like we have here, where we're trying to start in this little bottom left-hand square and wind our way up into this +1, there's really this notion of sequences of actions. So in the reinforcement learning context and all the things that we're talking about, at least in the foreseeable future, there's this sort of problem where you take some action and that puts you in some place, and then you take another action and that puts you in some place, and then you take another action and that puts you in some place, and maybe it puts you at a place where you get +1. Or maybe it puts you at a place where you get -1. And what really is going on here is this idea that you take actions that will set you up for other actions, that will set you up for other actions, and only then do you know how good those particular actions you took were. So this reward is not just an idea of getting a reward at every state, it's an idea of getting delayed reward. So you don't know how your immediate action is going to lead to things down the road. So let me give you a concrete example about that. So have you ever played chess?
Sure.
So let's say we played a long game of chess and maybe it took 60, 61, 62 moves. And then at the end, I win the game. So what do you know about the way you played that game?
That I probably made a bad decision around the time when I decided to play chess against you.
That's possible. But maybe you made a good decision and you kept making good decisions and you only messed up at the very last move. when you could have mated me, but you didn't.
I see. Well, my experience in playing chess is that's not what happens. Usually it's not that I make a bad move and then there's a problem. It's usually I make a move that I think is reasonable that only later I discover put me in a position where I can't possibly do anything good.
Right. Well, that's actually the game that I played in New York many, many years ago that I lost was exactly like that. The game went on for like literally 100 moves. I really lost the game on the third move.
Oh.
I made a mistake. I transposed 2 moves because it was a new opening that I was just learning. And I knew at the time that I screwed up. I played beautiful chess from that point on, but the truth is the other player had a positional advantage from that point on that I could never overcome. So I lost the game, but not because I played poorly for 80 moves. It's because I played poorly for 1 move, and that move happened to be fairly early. So this is this notion of delayed reward, that I played this long game of chess, and maybe I played well and I screwed up in the end. Maybe I played a mediocre game, but I had a couple of brilliant moves and that's why I won. Or maybe I played very well in the beginning, poorly at the end, or the other way around. And the truth is you don't really know. All you know is that you've taken a bunch of actions. You get rewards, signals back from the environment, like I won the game or I lost the game. And then you have this problem of figuring out of all the actions that I took, what was the action that led to me ultimately winning or losing or getting whatever reward that I got at the end of a sequence. Does that make sense?
Yeah, it seems like that could be really challenging. You probably need your own sportscaster listening and commenting.
Yeah, and in fact, the sportscaster who's listening and commenting, at least in the MDP world, is in fact the sequence of rewards that you get and the sequence of states that you see. Right? It really is sort of a play-by-play. In this state, took this action, got this reward. And you want to take all of that and then figure out whether this was a good action, your first action, or a poor action, or your second action was good or poor, and so on and so forth. Now, contrast that with supervised learning. So in supervised learning, what you would be getting is, well, I was in this state, this first state, and then this was the proper action I was supposed to take, let's say action 17. And your goal then is just simply to learn a function from states to specific actions. That's how the supervised learning problem is set up, right?
Yeah, exactly.
In this particular case, you're in some state, you take some action, and you get some reward for the action that you took, or maybe the state that you ended up in, or something. And you get a sequence of these state action reward triples, and then ultimately you have to figure out, for the given states you were in, what was the action you took that helped to determine, or actions you took that helped to determine the ultimate sequence of rewards that you saw. Perhaps this 1 + 1 or this -1 that you got at the end. This is a really difficult problem. It's got its own name. It's called the credit assignment problem. And in fact, because we're talking about a sequence of events over time, we typically refer to this sort of problem as the temporal credit assignment problem. Does that make sense, Michael?
Yeah, that's really cool. Although I guess it's credit, but also blame, right?
Well, credit and blame blame is just the minus of credit. So without loss of generality, assume that credit can assume a negative or positive value.
And yet when I go to the supermarket, they never say blame or credit.
Well, that's just because they don't understand the technical terms.
Got it.
We're really interested in solving this temporal credit assignment problem. As we will see as we talk later on in the course, this sort of issue comes up again and again and again. But I didn't really want to talk about that in any great detail. I just wanted to make certain that people saw the difference between supervised learning and the sort of problems that we're trying to solve now, that really it has to do with sequences and time. What I want to do is focus a little bit more on rewards. And in particular, I want to look at the little grid world that we've been playing with so far and think about how we would learn how to get from our start state, which we always started over here, over to one of the +1 or the -1, depending upon the kind of rewards that we see. So let's push on this rewards notion for a minute if we think about how NDPs are made up. And I'm just going to write down for you what the reward is for the states in this particular grid world, okay?
Yeah.
So let's say I'm going to set the rewards to be equal to -0.04. So the first thing I want to do is I want to make sure you understand what I mean by this. So what I mean when I write this down for this particular example is that the reward that I'm going to receive in every single state is -0.04, except, of course, for these two states, which I've already labeled as +1 and -1. Okay?
All right. So it seems like you should just never, ever move then, right?
No, I don't think that's true. Let's think about that for a little while. So if I set this reward to be -0.04, and you're starting out here in this state, and you have to keep living, you always have to take an action, right? That's the way I've set this up. And you don't get to stop until you reach either +1 or -1. We'll call these terminating or absorbing states. Once you reach into one of these things that ends the game, what would having a small negative reward like this encourage you to do?
It's making me think about kind of walking across a hot beach. Because like each time you take a step, you're going to get a little bit of punishment. And the only thing that ends it is if you can get into that nice, cool ocean. And then you get a +1 for that and the -0.04s stop.
Right. So that means, so wait, how would you put that another way? It sounds to me like what you're saying is by having a small negative reward everywhere, it encourages you to end the game.
Yeah. Yeah, I agree with that.
Okay, yeah, and I think that's exactly right. I like that analogy a lot. You're in well, it's not a very hot beach. It's just a, slightly unpleasantly warm beach. And you really want to hurry up and get into the ocean. And in fact, you want to hurry up and get into the ocean, even though on your way to getting to the ocean, you might step on some glass. The -1 is. So let's go back to this notion of policy, of mapping states to action. And let's think about us being in this world where you have a reward of -0.04 everywhere except in the absorbing states. What do you think the best set of actions are to take in these different states? What do you think the best policy is? Actually, before you tell me, let me write down what the actual policy is. I'm not going to tell you how we get here, but I'm about to write down the policy that's sort of the best one to take in a world where you have these sets of rewards. Okay?
Sure.
Okay, you see this, Michael?
Yeah, and it makes a lot of sense. Like if you're basically heading towards the rewarding state, the green state.
Right. So if I start out here in the leftmost bottom state, basically it says go up and then go to the right, which coincidentally is the policy that we had found before.
Cool. There's a couple spots that are a little bit strange, though.
Like what?
Well, I'm thinking about the one not directly under the -1. That makes sense to me. But the one, it takes you now to a position where it seems like you want to go straight up to the goal, but yet it's going the long way around. It just didn't see the goal?
No, that's not it at all, because the way we're going to learn this, so this is a global policy, and I'm just telling you that it's the optimal policy given the rewards. So let's kind of work out why going to the left makes sense here. Well, so here's my argument. What this basically says is take the long way around. Yes?
Yeah.
But by taking the long way around, what's happening? Well, on the downside, I'm going to pick up a little bit of negative reward for a while. 1, 2, 3, 4, 5, 6 or so, which is something like -0.2, -0.3, something like that, right? But by doing this, I avoid ever getting into a state where I might fall into the -1.
Ah, because it's stochastic.
Right, it's exactly. The stochasticity means that if I'm in this state here, no matter what I do, if I go up, I have some chance of moving to the right and falling into the -1. It's a relatively low chance, it's only 10%, but it works out that moving from here to here, the probability of me falling into here is too high compared to the sort of near impossibility of me ending up falling into -1 if I can follow this path.
Interesting. Okay, I guess that makes sense. That's cool.
Which actually suggests sort of the point that I want to make here, which is that minor changes to your reward function actually matter. So if we had a slightly different reward here, say not -0.04, but something else, you might find that some of these decisions would be different. Think you can see that?
I mean, at the level that I'm understanding it, it seems like if it's 0, then it's in no particular hurry. If it's minus something big, then maybe it's in a bigger hurry. But I don't see exactly what the difference is going to be.
Okay, so let's see if we can help you see the difference by making you take a quiz.
Aha!
Okay, Michael, so here's the quiz. Are you ready?
Sure.
Okay, so here's what's going on. I have copied over our little grid world over here twice. So it's the same grid world, except I have changed the rewards that you will receive in all of the states other than the 2 absorbing states. So for the top one, you get a reward of +2 in every single state except for the absorbing states. And in the bottom one, you receive a reward of -2 in every single state but the absorbing states. Got it?
Interesting.
So what I'm going to want you to do is I'm going to want you to fill in for these boxes that I've indicated, these same 4 boxes in the top and the bottom, whether you should go up, down, left, or right. So enter into each one of them either up, U, D, down, R, right, L, left. Okay?
Yeah, I appreciate you making the numbers nice and big because I was worried you were going to say something like -0.13. But this I think, no, that wasn't a suggestion. Yeah, let's go with the +2 and -2. I feel like there's a better chance I might be able to get it.
Okay, but so you think you got the what we're trying to do here?
I do. Now, just to make sure that I'm there, the +1 and the -1 end the game.
Yes.
And there's no more reward after that. It's like 0 forever.
Yep.
And the other things, the bluish rewards, I would get them continually until a state is reached.
Right, exactly.
Where the game ends. Okay, yeah. No, that's cool.
Okay, cool. All right, so go. Okay, Michael, you got answers for me?
Sure.
All right.
Wait, do I need to make any assumption, or can I make any assumptions I want about the non-blue states?
No. It doesn't matter. Actually, so the answer is
Maybe
no.
it does.
The answer is no, but it doesn't actually matter because, remember, it's all very stationary and Markovian, so the only thing that matters is where you are.
You're stationary, Markovian. All right, so I think okay. So let's do the first one then.
Okay.
So this is pretty cool. So by changing the reward the way that you did, it's not a hot beach anymore. It's like super awesome money beach.
Yes, it's like a beach made of bacon.
Sure. Okay, let's think of it that way. Though neither of us are eating bacon at the moment.
At the moment. I can
right, because then our mouths would be full and it would be very difficult to give this lecture. All right, so no. I mean, like even. All right, never mind. The point is that it's awesome and there's like diamonds. I don't know. I just saw the Hobbit movie and there was a room filled entirely with treasures, and so this is kind of like that. And so now the question is, what should I be doing? Like I should never go to the +1 or the -1 because that ends my treasure gathering. I should just continue to stay in states that aren't those states.
Okay.
So I would say left for the top state.
Mm-hmm.
Let's say left for the bottom state.
This one?
Okay. And the other two I need to think about for a moment. So I feel like I'd like to get away from the -1.
Mm-hmm.
So like, to go up. But then that would give me some chance of slipping, wouldn't it?
Mm-hmm.
Let's see. I don't want to go to the right. I don't want to go down. I'm going to go to the left.
Mm-hmm.
I'm going to bash my head against the wall because then I get money.
Yeah.
That's weird. There's really no pain for running into the wall?
Nope. You just stay where you are.
All right. And for the bottom one, I feel like it's the same kind of thing. I don't want to go to the right or to the left because then there's a probability that I'll slip and end up ending my game. So I'm going to go down.
Yeah. I like that. So most of these are right, and one of them is wrong. Or it's not that it's wrong. It's just it's not as right as it could be. Which one do you think that is?
I think they're right. But if there's one that I could imagine you not being so happy with, which is the bottom one.
There are two bottom ones. You mean this one?
Yeah.
Yeah? What would I like?
I think you might prefer if I bash my head against the wall.
No, actually, it turns out that this is a correct answer, so all four of these are correct. But in this particular state, it actually doesn't matter which way you go.
Oh, I see. A more complete answer
Yes.
would be doesn't matter.
Yeah.
And is that true of any of the other ones? No, I guess you're right. The other ones, you have to go in the direction indicated.
Right. So, by the way, just like here, it doesn't matter which direction you go in. It's actually true for all of the other states as well. It doesn't matter where you go because in these three states, these are the only states where you can end the game. And in each of them, you can take an action that guarantees that you don't end the game. So it really doesn't matter about where you do it in the other states.
Cool.
Right? So that's a good argument. This makes a lot of sense. So at the end of the day, basically, because the reward is positive and you're just accumulating reward or diamonds and treasure, as you put it, you just never want to leave. So you always want to avoid either of these states. It doesn't matter that there's a positive one here and a negative one here. If I can stay here forever, then I just accumulate positive reward forever. Okay, so what's the next one?
So interesting. So now the beach is really, really hot. It's -2. So I want to get off here as quickly as I can. So definitely the top one, I would go to the right and just try to get that +1 and get out of here.
Yeah.
All right. So then let's think about the bottom right.
Okay.
So in the best of all possible worlds, I go around and dump into the +1. So that would take me, again, if I don't slip at all, 1, 2, 3, 4 steps to do that. Actually, wait, 1, 2, 3. 3 steps on the hot sand.
Yep.
And I'm getting a -2 for each of those. So that's like -6. So I could get that +1 at the end, and that makes it only -5. but I think I'd rather just get off the beach. So I'm going to say in the bottom right to actually dive into the pit of pain because it can't be as bad as where I am.
That's exactly right.
So, okay, so then the one next to it on the left is a little trickier. If I go up to the +1, I get a -2 followed by a +1, which is also a -1.
Mm-hmm.
So, okay, I'm not so sure about that one.
Well, remember, you'll always have some probability of ending up back where you started.
Is that true? Oh, because well, no, that's not true. If I dive straight into the -1, then I have 0.8 chance of going to the -1, 0.2 of going up to the arrow that's labeled, 0.2 going down to the blue box that's not labeled.
Mm-hmm.
Wait, 0.2? No, 0.1.
Mm-hmm.
Whereas if I go up, right, I might stay where I am and accrue -2. Like, yeah, I feel like I need a calculator for this.
Yeah, but I think your intuition is right, though. Just think about it as how much, what do you think has the best chance of most quickly ending things?
Well, certainly jumping into the -1.
Right.
I think that's going to be marginally better because there's only one chance of slippage and delay, whereas if I take an additional step, there's 2 chances of slippage and delay.
Exactly. That's exactly the right kind of argument to make. And because the -2 is so big, you're just better off ending it even if you ended in pain, in the same way that you were in the bottom right-hand corner.
And so bottom left, I would say the cleanest thing would be to jump into the -1. So to go to the right so that I can go up and get into the -1.
And what's nice about that move is that you either end up in the bottom right-hand corner, or you end up staying where you are, or you end up moving up. But in either case, you are always sort of, you never get farther away, right? Whereas if you tried to go up, there's a chance that you would get farther away.
Interesting. Is there a way to be sure about these?
Yeah, you just have to do the math.
Do we know how to do the math?
Yeah, you just do expectations. You can basically just say, well, what's the expected time? Since you know what you're trying to do here is to get to the end, you could calculate the expected length of time it'll take you to get there. And then just, multiply by all the rewards you're going to get in the meantime. If it helps, though, I will tell you that for any value where the reward is less than -1.6284, this is the right thing to do.
Okay.
Just so you know.
All right. So you're saying you actually do know that this is the optimal, the thing that we have written.
Yes, I know that this is the optimal.
All right.
Let me just draw out the rest of it for you. So it's I think interesting to compare this one, the bottom right one, where you've given me negative reward to encourage me to end the game, with our main one up here in the upper left, where you've also given me some negative reward to encourage me to end the game. If you look carefully, you'll notice that in this one, you're encouraged to end the game, but you're really encouraged to end the game at a +1. Here, the reward is so strongly negative, you just need to end the game. And so you end up with a different response here, because it's just as quick to get to the -1 and end your pain as to take this extra step and try to get to the +1. And you end up with a different response here, 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 and here.
That's really interesting.
Yeah, it is. And so these changes matter. And they matter a great deal.
So how am I supposed to choose my rewards?
Carefully and with some forethought.
Nice.
But, again, there's lots of ways to think about this. So the way we've been sort of talking about MDPs is kind of the way we've been talking about. We talked in the first part of the course when we talked about having teachers and learners. You can think of your reward as sort of the teaching signal and sort of the teacher telling you what you ought to do and what you ought not to do. But another way of thinking about this is that because the rewards define the MDP, the rewards are our domain knowledge.
I see.
So if you're going to design an MDP to capture some world, then you want to think carefully about how you set the rewards in order to get the behavior that you wish.
That's fair. I mean, it seems a little bit like a cop-out, but I think it seems like a necessary one.
Yeah, again, no matter what you do, you've got to be able to inject domain knowledge somehow, or otherwise there's no learning to do. And in this case, the reward basically is telling you how important it is to get to the end.
Cool.
Okay. All right. Let's move on. All right. So having gone through that exercise, Michael, I think it's worthwhile to step back a little bit and think about the assumptions that we've been making that have been mostly unspoken. And I'm going to say that the main assumption that we've been making in some sense boils down to a single word, and that word is stationarity. So let me tell you what I mean by that and why, by kind of illustrating what it is we've been sort of doing for a little while. Okay?
Sure.
Okay. So the first thing I'm going to say is that we've actually been kind of assuming infinite horizons. So what do I mean by that? When we think about the last grid world that we were playing with, we basically said, well, I want to avoid going to the end as quickly as possible if I have rewards of a certain value or whatever, because, the game doesn't end until I get to an absorbing state. Well, that sort of implies that you basically can live forever, that you have an infinite time horizon to work with. Now, can you imagine why, if you didn't have an infinite time horizon to work with, you might end up doing something very different?
Different than what we were doing in the grid world.
Right. So here, let me show you the game that we were the grid world that we were doing before. Might help you to think about it. So here's the grid world we had before, and as you'll recall, we had a particular policy that sort of made sense. Here, I'll write it out for you again. And this was with a case where we had a reward of minus 0.04. Remember? We just did this. Remember?
Yep.
Okay. And this was the policy that turned out to be optimal. And the feature I want you to pay attention to here is that when you're over right here near possible end state, rather than going up, it made sense to take the long way around because you were going to get some negative reward, but it's a small enough negative reward compared to where you might end up, okay, with a positive one.
Yeah, I see. Uh-huh.
And that makes some sense. Well, that only makes sense if you're going to be living long enough that you can afford to take the long route around. What if I told you only had, say, 3 time steps left, and then the game is going to end no matter where you end up?
Well, it might make more sense to take some risk and to just try to take the short way, because otherwise there's really no chance you're going to get to the +1. I'm not entirely convinced of that, though, because there's still a chance that you'd fall into the -1 along the way.
Right. So the exact value, whether it makes sense to take the risk or not, is going to depend upon 2 things. We've already talked about one of them, which is the actual reward that you get. If this reward were, negative enough, then clearly it makes sense to just try to end things quickly, right? We just showed that in the last quiz. But the other thing it's going to depend upon is how much time you have in order to get to where you're going. If you've only got 1 or 2 time steps before everything's going to end, you can imagine that there are cases where, without changing the reward too much, it makes a lot of sense to try to go ahead and quickly get to this +1, even though you have some chance of falling into the -1. As opposed to trying to move away where you're then kind of all but guaranteed that you're never going to reach the +1. So whether it makes sense to take the risk or not will depend upon the reward, but it's also going to depend upon whether you have an infinite amount of time to get to where you want to get to, or whether you have a finite amount of time. And the real major thing that I want you to get out of that is that if you don't have an infinite horizon, but you have a finite horizon, then 2 things happen. One is the policy might change because things might end. But secondly, and more importantly, the policy will change or can change even though you're in the same state. So if I told you, if you're in this state right here, and I told you you didn't have an infinite amount of time, but you still had 100 million time steps, then I think it's clear that it still makes sense to go the long way around, right?
Yeah, I mean, the probability that this policy is going to last for 1 million time steps has got to be tiny.
Right. So I might as well, it's 100 million time steps might as well be infinity. But if I make that number not 100 million, but I make it 2 or 3 or 4, then suddenly your calculus might change. And in particular, your calculus will change even though I'm in the same state. Right? So maybe this state right here, if I've got 100 million time steps, I still want to go the long way around. But if I've only got a few time steps, the only way I'm going to ever have a chance of getting positive reward is to go this way. Does that make sense?
I guess so. So you're saying, for example, even within a single run, it could be that I'm in a state and I try an action and maybe it doesn't work and I stay where I am, and I try it again and maybe it doesn't work and I stay where I am. It might then switch to a different action, not because the other one wasn't working, but because it's now running out of time.
Right, exactly. So we talked about this notion of a policy which maps states to actions. And we talked about this notion of stationarity. So you believe that in this sort of Markovian thing said, well, it doesn't matter where I've been, it only matters where I am. And so if I'm in this state, since it only matters where I am, I'm always going to want to take the same action. Well, that's only true in this kind of infinite horizon case. If you're in a finite horizon case, and that finite horizon, of course, is going to keep counting down every time you take a step, well, then suddenly, depending upon the time step that's left, you might take a different action. So we could write that, I think, just for the sake of kind of seeing it as something like, your policy is a function of both the state you're in and the time step you're in. And that might lead you to a different set of actions. So this is important. This is important. I mean, we are not for this course going to talk about this case at all, where you're in a finite horizon. But I think it's important to understand that without this infinite horizon assumption here, you lose this notion of stationarity in your policies. Okay?
Yeah, interesting.
Okay. So that I think is, maybe not something that's obvious, but becomes obvious after someone points it out to you. So the second thing that I want to talk about, I think, is a little bit more subtle, and that's this notion of utility of sequences. So as we've been talking, Michael, we have been sort of implicitly discussing not just the rewards we get in a single state, but the rewards that we get through sequences of states that we take. And so I just want to point out a little fact that that comes from that and where that ends up leading us, and then we'll get to some nice little cute series of math. So here's what I want to point out, what we mean by utility of sequences. It means we have some function, I'm going to call U for utility, over the sequence of states that we're going to see. Let's call them S0, S1, S2, and so on and so forth. Well, I think an assumption that we've been making, even if we haven't been very explicit about it, is that if we had two sequences of states, S0, S1, S2, ... and a different sequence, S0, then S1 prime and S2 prime. That is two sequences that might differ from S1 on, but all start in the same start state, okay? If we have a utility for the first, and that utility happens to be greater than the utility for the second, then it also turns out that we believe that the utility for S1, S2, ... is greater than the utility for S1 prime, S2 prime, ...
All right, so these are two different sequences. S1, the S's and the S primes are two different sequences.
Yes.
And in the beginning, we're comparing them with S0 stuck in front of both of them.
Yes.
And we're saying if I'd prefer the S0 followed by all the S's to S0 followed by the S primes, then I have that same preference even with those S0s missing.
Right. And so this is called stationarity of preferences. And another way of saying it is that if I prefer one sequence of states today over another sequence of states, then I prefer that sequence of states over the same sequence of states tomorrow.
So isn't this just obvious? Because whatever the rewards are for those two cases, we're just adding the reward that we get for S0. So it's going to be the same.
But listen to what you just said. You just said, well, it'll be the same because all we're doing is adding the reward for S0. But what did we ever say about adding up rewards?
I thought that's what we were doing.
That's right. That is what we were doing. But we never actually sat down and wrote that down and said, this is what it means to talk about the utility of a sequence of states as opposed to the reward that you get in one state.
Okay, so you're saying that if we are adding rewards, then this follows.
Right.
Okay.
And then I'm actually even saying something even stronger, which is, I will show you on the next slide, which is, if you believe that this is true, that the utility of one sequence of states is greater than the utility of another sequence of states, both today and tomorrow, then it actually forces you to do some variation of what you said, which is just adding sequences of states, or adding the rewards of the sequence of states that we see.
That's really interesting. So the adding isn't really an arbitrary thing. It follows from this deeper assumption.
Right. And, the reason I bring this up is because it would make sense if you were just to grab someone off the street and start talking about Markov decision processes. One of two things would happen. Either they'd run screaming from you like you're a crazy person, or they would sit and they would listen. And if they listened, they would just completely buy into the idea that you just add up sequences of rewards that you see as a way of talking about how good the states are, because that's a very natural thing to do. But it turns out that mathematically, that if you have this notion of sort of stationarity of preferences and this sort of infinite horizon world, you really are in a case where this has to be true. And it has to be the case that you have to do some form of addition, because nothing else sort of can be guaranteed to maintain this property over stationary preferences. I mean, as you said, if I got one sequence of states and another sequence of states, and by just prepending or appending another set of states to it, I'm still going to always guarantee that one's greater than the other. You kind of have to do some form of adding the reward that you see in those states in both cases. Because if you don't do that, then eventually this inequality will not hold. So let me write that down in math terms and see where it gets us, okay?
Cool.
All right, Michael, so let's write that down in math, okay? You like math, right?
I do.
Okay, so here's the math version of it. I'm going to just say that the utility that we receive for visiting a sequence of states as 0, as 1, as 2, ellipsis, is simply the sum of all the rewards that we will receive for visiting those states.
Sure.
Does that make sense?
Yeah.
Is that consistent with what you were doing when you were thinking about the grid world?
Yeah, exactly. But I thought we were going to make that not definitional. We were going to derive that it had to be that way.
No, we're not. They can read about it. It'd take me like an hour and a half to do that.
All right.
And I'm already losing my voice. But what I want you to believe is that the utility of the sequence of states, thinking of it as the sum of all the rewards, makes sense, right? And if nothing else, at least it's consistent with what you've been doing as we've been talking about this grid world.
Yeah, absolutely. I mean, it also kind of makes me think about money.
Go on.
Well, so I mean, that's sort of how money works. If we get some kind of payoff each day, those payoffs get added to each other. They don't get, subtracted or multiplied or square rooted or whatever. They just, they go into your bank account and things add. So this feels like kind of like that. It's like money in my pocket.
Sure, if you have a big enough pocket. Okay, I'm with you on that. All right. So I'm going to say that this all makes sense. It's really awesome, and it sort of doesn't work.
What?
And to illustrate why this doesn't work, I'm going to give you a quiz.
Yay.
Because you like quizzes.
So I've been told.
So here's the quiz. You see on the screen this sort of unexplained two little squiggles with a bunch of numbers in front, on top of them, or under them, or near them?
Yeah, I assume that's a river, and on one bank it's the land of the +1s, and the other bank has been infiltrated by +2s.
That's not what I intended at all, but I actually like that enough that I'm going to pretend that that's what I intended. So these work out to be sequences of states.
Oh, I see now.
And rewards that you receive. No. It's a river bank, and on one side of the bank, as you walk along it, you get a bunch of +1s, and on the other side, you get a bunch of +1s and some +2s. And this just goes on forever. Okay? And I'm not going to tell you what all the rewards are after that, except that they look similar to the rewards that you see here.
Okay.
+1s and +2s. Okay, and let's say the top one is in fact nothing but +1s, and the bottom ones are some +1s with maybe some +2s sprinkled in and out, but those are really the only options. Okay?
Yeah.
Here's my question to you. So, would you rather be on the top side of the riverbank or the bottom side of the riverbank? Okay? You think you know the answer already, don't you?
Yeah.
Okay, cool. Well, then let's give our listeners a chance to come up with their own answer. Okay, Michael, I didn't give you as much time as I normally do because you think you already know the answer. So what's the answer?
So, I'd rather get the +2s occasionally, so I'll say the bottom one.
No.
Wait, what? You're not going to tell me the top one's better?
No, it's not.
Okay, then that feels like a trick question.
It's not a trick question. The answer is neither one is better than the other.
Oh, so I had to give neither?
Or both.
Which is better, and I can click on neither.
Or you could click on both. Okay. So you thought that the bottom one was better. What was your reasoning for that?
Because sort of moment to moment, sometimes I'm getting +1s, and that matches what I would have gotten if I had been on the other bank. But then sometimes I get +2s, which is actually better than what I would have gotten on the other bank. And so I never feel any regret being on the bottom bank. I only feel regret being on the top bank.
That's fine. So what would you say the utility of the sequence along the bottom actually is?
1 + 1 + 2 + 1 + 1 + 2 +...
Which is equal to?
Infinity, I guess.
That's right. What about the utility of the top one?
1 + 1 + 1 +... That's also infinity.
Yep. So the utility of both of those sequences is equal to infinity. Do you think one of them is bigger than the other?
You drew the bottom one a little bit larger.
I did, or longer anyway.
Yeah.
But in the end, the sum of the rewards that you get are both going to be infinity. So the truth is, neither one of them is better than the other.
I still don't think you can say that both are better.
You can't get around that.
But yeah, I see neither. I could see neither is better.
Or that both are better. Neither is better, both is better, whatever. The point is that they're both equal to infinity. And the reason they're equal to infinity is because all we're doing is accumulating rewards. And if we're always going to be able to get positive rewards no matter what we do, then it doesn't matter what we do. This is the existential dilemma of being immortal.
Oh, living forever. So if you live
Right.
forever, then why should you care about anything ever?
Right. I mean, all the mortal people are going to die. And one day they'll all be, an infinite amount of time in your past. I could do this thing here, which is pleasurable, or I could do this thing right now that, is less pleasurable, but will eventually get me to a better place. But if I'm going to live forever and I can always get to a better place, then it really doesn't matter what I do. It really doesn't matter. because I'm just accumulating rewards. I'm living forever, and infinity is infinity, and there's really no way to compare them. Having said that, your original notion that, look, it feels like I should never regret having taken the second path compared to the first because I will occasionally do better, seems like the right intuition to have.
I see, but it's just not built into this particular utility scheme.
Right. But it turns out there's a very easy way we can build it into this utility scheme by just making one tiny little change. Would you like to see it?
Yes.
Beautiful. Let's see it then. Okay, Michael, so here's the little trick. So all I've done is I have replaced the equation at the top with an alternate version of the equation.
Okay. And it looks like you're now exponentially blowing up the reward.
I am not exponentially blowing up the reward. Instead, what I've done is I've added up the rewards that I'm going to see for the states that I'm going to see, and I multiplied it by gamma to the t, but gamma is between 0 and 1.
Ah, I see. So,
do you?
Well, kind of. So it doesn't exponentially blow up; it exponentially implodes.
Right.
So things that are like 1,000 steps in the future, if we take something that's less than 1 and we raise it to that power, it goes essentially to 0. So it's like it starts off, the rewards are kind of substantial, and then they trail off quickly.
Right. And in fact, we can write down mathematically what this is. You actually, if you stared at it long enough and you remembered your intermediate algebra or your calculus or wherever it is you learned this stuff, you would probably recognize this as a special kind of sequence or series. Do you remember what it is?
Television series?
No, but that's remarkably close. So let's see if we can bound this particular equation. So we know that this version of the equation eventually ends up being infinity if all the rewards are positive, right?
Mm-hmm.
So what does this end up being even in the case where all the rewards are positive? Well, we can bound this from above by the largest reward that we will ever see in the following way. So all I've done is said, well, I don't know what the rewards are, but there is some maximum reward. I'm going to call it R max. And if I pretended that I always got the R max reward, as long as that's an actual number, a finite number, I know that this is bounded from above by this expression. Well, what does this look like? Maybe this does look like a series you remember.
Geometric series?
Yes, this is the geometric series, and this is exactly equal to this.
And I assume that the summation causes the max to become lowercase?
Yes, it does. That's a trick that they don't really go over deeply in calculus, but it's true.
Oh, that's cool. All right, so the maximum reward divided by 1 minus gamma. So when gamma is really close to 0, you're getting just that one reward in the beginning, and then everything falls off to nothing after that.
Yep.
And if gamma is really close to 1, you're dividing by something that's teeny tiny, which actually is like multiplying it by something that's really big. So it kind of magnifies the reward out. But it's not infinity until gamma gets all the way up to 1, and that's the same case we were in before.
Right. So in fact, you'll notice the way I wrote this, gamma has to be between 0 and 1, 0 inclusive, but strictly less than 1. If I made it so that it could include 1, well, that's actually the first case.
Got it.
Because 1 to a power is always 1. And so this is actually a generalization of the sort of infinite sum of rewards. This is called discounted rewards or discounted series or discounted sums. And it allows us, it turns out, to go an infinite distance in finite time.
Wait.
If that makes sense.
No.
Well, it does.
An infinite distance?
Yeah, that's at least the way I like to think about it. So if we're discounted in this particular way, then that gives us a geometric series. And what it does is it allows us to add an infinite number of numbers, but it actually gives us a finite number.
Cool.
So this means we can still have and it turns out, by the way, just to be clear, that this world that we're in, where we are in between 0 and 1, 0 inclusive, is still consistent with our infinite horizons and our stationarity over preferences. So we can add things together and be consistent with those assumptions we were making before, or we can do discounted rewards and we're still going to be consistent with what we're doing before. But the difference between this case and this case is that by doing the discount, we get to add infinite sequences and still get something finite. The intuition here is that if gamma is less than 1, then eventually as you raise it to a power, it will basically become 0. I mean, that's why it's a geometric series, which is like having a finite horizon. But that horizon is always the same finite distance away no matter where you are in time, which means it's effectively infinite. or unbounded, or however you want to think about it.
So it's like you take a step, but you're no closer than when you started.
Right. So what does that mean in a world where you meant to say you're no closer to where you were trying to end up? So that means that even though you've taken a step forward, the horizon sort of remains a fixed distance away from where you are.
Mm-hmm.
That's what it means to have this kind of this gamma value here. And so you can still treat it as if it's always going to be infinite, even though it gives you a finite value, and that gives you your stationarity. So does that make sense? I mean, that's sort of the intuition that you really are having, you're always an infinite, it's always infinity, but the gamma value means that at any given point in time, you only really have to think about what amounts to a finite distance. You never get closer to the horizon, even though you're always taking steps towards it. But there still is a horizon that you can see, if I can kill that analogy.
So can you explain to me why it has this form, this Rmax over 1 minus gamma?
I could. You can kind of prove that in a little cute math way, and I'm happy to take that diversion if you want.
Yeah, I think so.
Okay.
I mean, unless you were going to tell me something else.
Well, how about I tell you something else, and then I take that diversion?
Okay.
Okay, so here's something else. In the beginning I said, this is like going an infinite amount of distance in finite time, which you rebelled against. And my explanation is more about how infinity looks finite, which is not the same thing as going an infinite amount of distance in finite time. The reason I said that is because of the singularity.
What?
The singularity. So some of our listeners no doubt have heard of the singularity. Have you never heard of the singularity?
The singularity is like when computers get so fast that you can do infinite computation in... Oh.
Right. So the singularity, for those of you who don't know, is this sort of observation that has been made by many folks that the sort of limit to computer power growing faster is the fact that it takes us some amount of time to design the next generation of computers, right? So Moore's law says everything doubles, every 18 months or whatever. But if we could design things faster, then we could actually make it double more quickly. So one day we'll get to the point where the computer, which I will draw here like that, the computer can actually design the next generation of computer. Well, when it designs the next generation of computer, that computer will also have the ability to design the next generation of computer, but it will be able to design it twice as fast. And then the next one will be able to design its successor twice as fast, and so on and so forth. So this little time between generations will keep having every single time, which looks remarkably like a geometric sequence. And so once we reach this point where the computer can actually design its successor, we will then be able to do an infinite number of successors in finite time. And that's when the world comes to an end, and that's what's called the singularity, because we can't understand what happens after that point. So that's what I mean by going an infinite amount of distance in finite time.
It just doesn't seem like distance, but yeah, that's a weird example.
I think it makes sense.
An infinite number of doublings in it. Yeah, no.
Well, we'll do some assignment where we allow people to decide whether this makes sense or one of your analogies makes sense. And I'll just remind the listener that I'm the one who'll be assigning final grades. Okay, so with that, let's go and do your little diversion, and then we'll come back to doing a whole lot of math. So I actually think this little nice diversion will be a warm-up to all the math we're going to be doing. Okay?
Ooh, more math.
So if we think about the equation that we were doing before, which was, the sum of all these gammas times some Rmax, we can basically take out the Rmax, and what we end up with is something that looks like that, right? You're summing together a bunch of gammas and then multiplying the result by Rmax. So what does that actually look like? Well, that looks like this. Gamma to the 0 plus gamma to the 1 plus gamma squared plus ... eventually multiplied by Rmax, right?
Mm-hmm.
So let's call this x, okay?
Does x include the Rmax or not?
No. So we'll just call the little sequence of it's going to turn out not to matter, but let's just call the sequence of gammas that we're adding together, let's just call that x.
Good.
Well, if you look at it, this is actually recursive, right? because it's an infinite sequence, if you sort of shifted it 1 over in time, you would end up with just the repeated sequence again, right? Which means that we can write x in terms of itself. X equals gamma 0 plus gamma times x.
I see. So it's shifted over, but then you have to multiply it again by gamma to get up to gamma 1, gamma 2.
Right, exactly. So this is just, it's just math. That's just all it is. So we can try to solve for x and figure out what x is, right?
Cool.
So what is x? Well, we can subtract from both sides, and so we end up with like something like x minus gamma x equals gamma 0, right?
Seems like we can stop writing gamma 0. Isn't that just 1?
Yes, but I've gone too far, Michael. I've already written gamma 0. So this becomes x times 1 minus gamma equals gamma 0, or as Michael so astutely points out, 1, right? Which means what? It means that
So then we divide by 1 minus gamma.
x is 1 over 1 minus gamma.
Neat.
And
I
that,
see.
of course, we're going to multiply by our max.
And get the formula that we had. That's nifty.
Yeah, there we go. So why do we do this? Well, because you like stuff like this. And it points out something very simple, which is that geometry is easy.
I don't think that's the kind of geometry that people usually think of.
Well, they should be thinking of this kind of geometry. So geometry is easy. And by doing little cute algebra, we can derive ridiculous equations that turn out to help us go an infinite distance in finite time.
I don't think that's what they're doing, but okay.
So let's think of this as warm up for what I actually wanted to show you, which is going to turn out to be a whole lot of math. Okay?
All right, let's go for
All
it.
right, let's do that. Okay, so Michael, in the spirit of what we just went through in deriving the geometric series, I'm now going to write down a bunch of math. And what I'm going to do is I'm just going to say it at you, and you're going to interrupt me if it doesn't make sense. Okay?
That makes sense.
It does. Okay, so here's the first thing I'm going to write down. I've decided that by going through this exercise of utilities and discounted reward, we can now write down what the optimal policy is. The optimal policy, which as you recall is simply pi star, is simply the one that maximizes our long-term expected reward, which looks like what? Well, it looks like this. There, does that make sense?
Let me think. So we have an expected value of the sum of the discounted rewards at time t, and given pi, meaning that we're going to be following pi.
Mm-hmm. So these are the sequence of states we're going to see in a world where we follow pi. And it's an expectation because things are non-deterministic, or maybe non-deterministic.
And do we know which state we start in?
It doesn't matter. It's whatever S0 is.
I see. Whatever S0 is, but isn't that random? I mean, S1 and S2, S3, those are all random.
Well, we start in some state. It doesn't matter. So t is starting out at 0 and going to infinity. Okay? So does this make sense?
Yeah, so we're saying I would like to know the policy that maximizes the value of that expression.
Right.
So it gives us the highest expected reward.
Right.
Yeah, that's the kind of policy I would want.
Exactly. So good, we're done. We know what the optimal policy is, except that it's not really clear what to do with this. All we've really done is written down what we knew it was we were trying to solve. But it turns out that we've defined utility in such a way that it's going to help us to solve this. So let me write that down as well. I'm going to say that the utility of a particular state, okay? Well, it's going to depend upon the policy that we're following. So I'm going to rewrite the utility to take as a superscript pi. And that's simply going to be the expected set of states that I'm going to see from that point on, given that I follow a policy. There, does that make sense?
Feels like the same thing. I guess the difference now is that we're saying the utility of the policy at a state is what happens if we start running from that state.
Yep, and we follow that policy.
Got it.
Right? So this answers the question you asked me before about, well, what's S0? Well, we talk about that in terms of the utility of a state. So how good is it to be in some state? Well, it's exactly as good to be in that state as what we will expect to see from that point on, given that we're following a specific policy where we started in that state. Does that make sense?
Okay. Yeah.
Very important point here, Michael, is that the reward for entering a state is not the same thing as the utility for that state, right? And that in particular, what reward gives us is immediate gratification or immediate feedback. Okay? But utility gives us long-term feedback. Does that make sense? So when a reward for a state is the actual value that we get for being in that state. The utility for a state is both the reward that we get for that state, but also all the reward that we're going to get from that point on.
I see. So, yeah, that seems like a really important difference. Like if I say, here's $1, would you poke the president of your university in the eye? You'd be like, okay, the immediate reward for that is 1, but the long-term utility of that could be actually quite low.
Right. On the other hand, I say, well, why don't you go to college? And you say, but that's going to cost me $40,000. Or better yet, why don't you get a master's degree in computer science from Georgia Tech? And you say, but that's going to cost me $6,600. Yes, but at the end of it, you will have a degree. And by the way, it turns out that the average starting salary for people getting our master's degree versus our undergraduate degree is about $45,000.
So is it considered product placement if you plug your own product within the product itself?
No, I'm just simply stating facts, Michael. This is all I'm doing. It's just facts.
All right.
This is called fact
All right.
placement. The point is, there's an immediate negative reward of, say, $6,600 for going through a degree, or maybe it's $10,000 by the time the 15th person sees this. But anyway, it's some cost. But presumably it's okay to go to college or go to grad school or whatever, because at the end of it, you're going to get something positive out of it. So it's not just that it says it prevents you from taking short-term positive things if that's going to lead to long-term negative things. It also allows you to take short-term negatives if it's going to lead to long-term positives.
That makes sense.
Right. And what this does is this gets us back to what I mentioned earlier, which is this notion of delayed reward. So we have this notion of reward, but utilities are really about accounting for all delayed rewards. And if you think about that, I think you can begin to see how, given you have a mathematical expression for delayed rewards, you will be able to start dealing with the credit assignment problem.
Cool.
Okay, so let's keep going and write more equations. So now that we've got utility defined and we've got this pi star defined, we can actually do an even better job of writing out pi star. And let me do that. All right, so does this equation make sense, Michael?
Let's see. So the policy, is that a star again, or is that a K?
That's a star. So it's the optimal policy.
All right. The optimal action to take at a state is, well, look over all the actions and sum up over all the next states. The transition probability, right? So that's like the probability that we end up in state S prime.
Mm-hmm.
And now we have the utility of S prime. The problem being that that's not defined.
Well, it sort of is. We've defined it immediately above, at least with respect to some policy.
Yeah, but that's concerning because we don't know. I mean, the policy that you want to put in there is got to be the policy that you're trying to find.
Right. So, in fact, implicitly what I mean here is pi star. So,
Yeah.
in fact, let me write that down, that whenever you see me write from now on the utility of a state, I'm almost always going to actually mean the utility of the state if I follow the optimal policy. We might call this the true utility of a state.
I see.
So I'm just going to write this off to the side here as something for you to remember. So this says then that the optimal policy is the one that for every state returns the action that maximizes my expected utility.
With regard to the optimal policy, it feels rather circular.
It is rather circular, but you're a computationalist. You're a big fan of recursion. We just went through a whole exercise where we figured out the geometric series by effectively doing recursion.
It's a similar kind of situation for this?
It kind of is. So let me write one more equation down, and then you'll be one step closer to actually seeing it. Of course, if we're in an infinite horizon with a discounted state, even though you're one step closer, you won't actually be any closer. Well, let's worry about that when we get there. So let me write one more equation down.
We're never going to get there. It's infinitely long.
Yeah.
Wait, are you demonstrating something with this lesson by making it infinitely long? We keep.
I'm certainly demonstrating something with this lesson. I don't know what it is. So let me write this next equation down. So then the true utility of a state, S, is then I'm just basically going to unroll the equation for utility. It's the reward that I get for being in that state, plus I'm now going to discount all of the reward that I'm going to get from that point on. Got it?
All right. So once we go to our new state S prime, we're going to look at the utility of that state. Okay, that's sort of fine, modulo the recursion. We're going to look at over all actions, which action gives us the highest value of that. Oh, I see. That's kind of like the pi star expression just above.
Yep.
Then, all right, so once we figure that out, we know what action we're going to take in state S prime. We're going to discount that because why? Because I guess that it just kind of ups the the gamma factor on all the rewards in the future.
Right.
And then we're going to add to that our immediate reward. Yes.
Right. So
Okay, I think I followed
yeah,
that.
so in some sense, all I've done is I've kept substituting pieces back into one another. So the true utility of being in a state is the reward you get in that state plus the discount of all the reward you're going to get at that point, which of course is defined as the utility you're going to get for the states that you see, but each one of those is defined similarly. And so the utility you'll get for S double prime, say, will also be further discounted, but since it's multiplied by gamma, that'll be gamma squared, and then S triple prime will be gamma cubed. And so that's basically just unrolling this notion of utility up here.
Okay, so now it seems like all the pieces are in one place.
Right. And so it would be nice if we were done. And I'm going to say that we're not just one step closer, but you can see an oncoming light, and it is not an oncoming train. Okay? So
Yeah, this seems like a really important equation.
it is. In fact, it's so important it's got a name. You want to guess what the name is?
Bill.
That's actually very close. It's Bellman. It's Bellman equation.
Bellman equation.
Esquire. This equation was invented by a guy named Bellman, and it turns out to be, in some sense, the key equation for solving MDPs and reinforcement learning.
Wow.
And it's actually even more subtle than it looks. But basically, this is the fundamental recursive equation that defines the true value of being in some particular state. And it accounts for everything that we care about in the MDP. The utilities themselves deal with the policy that we want to have. The gammas are discount, all the rewards are here, the transition matrix is here, and the actions are all the actions we're going to take. So basically the whole MDP is referenced inside of here and allows us, by determining utilities, to always know what's the best action to take. Well, it's the one that's going to maximize the utility. So if we can figure out the answer to this equation, the utilities of all the states, we perforce know what the optimal policy is. It becomes very easy. So we've sort of taken all that neat stuff about MDPs and stuck it in a single equation. Bellman was a very smart guy.
So he's the same Bellman from the Curse of Dimensionality?
Yes.
Cool.
There can be only one Bellman. Actually, are there any more Bellmans? I don't think so. I think that they retired. It's like retiring a jersey. They retired his name.
I could have sworn that I saw one at the last hotel that I went to.
It's probably the same one. Oh, I get it. Hotel, Bellman. That's really good.
There we go.
Okay, good. Well, so now that we've killed that as much as we could, let's see if we can actually solve this equation, which, since this is clearly a key equation, since it has a name. Okay?
Yeah, that would be cool, especially because it looks like if you could solve this, you could solve it, right? Because then you have U. You can just plug the U in and get the U out.
Right, and once you have the U in and you get the U out, then you got the policy.
Right.
For you.
It's always been for you.
It's for us, Michael. It's for us. Okay, Michael, so I've erased the screen and kept Bellman's equation, the most important equation ever, and we are going to solve it.
Ooh.
So how are we going to make that work? Okay, so how many, so we wrote this down as a utility of S. How many S's are there?
S, N, M, I don't know.
Pick a letter.
N.
N. So we have N states, which means this isn't really one equation. This is how many equations?
N.
Yes, it's N equations. How many unknowns are there?
Well, we have a U. The R's are known. The T's are known. The only thing that's missing is the U's, and there's N of those as well.
Right, so there's N equations, N unknowns.
So we're done.
Yes, because we know how to solve N equations and N unknowns, right?
If the equations were linear.
If the equations are linear. Are these equations linear?
I'm going to go with no.
Why not?
Because the max is problematic.
That's right. This max operation makes it nonlinear. So it looks really good for a moment there. We've got N equations, N unknowns. We know how to solve that. But max makes for a very, very, very weird nonlinearity. And there's kind of no nice way to deal with this. Actually, one day, Michael, if you ask me, there is a cute little aside you can do where you can turn max into something that's differentiable.
Ooh.
But that doesn't actually help us here. So I'm not going to go off on that aside yet.
But even differentiable wouldn't quite be linear.
That's right, and it wouldn't help us in this case. That's exactly right. But the fact that you can have differentiable max is, I think, actually rather cute, but also unimportant for what we're talking about now. So we've got N equations and N unknowns. They're nonlinear, which means we can't solve it the way we want to by like inverting matrices or anything like you people who are into regression would normally do. But it turns out that we can, in fact, do something fairly similar, something that actually allows us to solve this, even though it's nonlinear. And here's the equation, here's the algorithm that you use that sort of works, okay? So it's really simple. Just simply start with some arbitrary utilities.
Declare those the answer, and you're done.
That would be one way of doing it, but it turns out we can do even better.
Wait, start off with the correct utilities.
That would work, except we don't know what they are.
Oh, right.
So we're going to start with some arbitrary utilities, but then we're going to update them based on their neighbors. And then we will simply lather, rinse, repeat.
All right, so what does that mean based on neighbors?
So it means based on the states, you're going to update the utility for a state based on all of the states that it can reach. So let me write down an equation that tells you how to update them, and then maybe it'll be clear. Okay.
Yep.
So we're going to have a bunch of utilities. Since we're going to be looping through this, and let's just say every time we loop through, that's time t. Okay. So we know what the equation for utility is. For the utilities are, it's just the equation that's written up here. So it's R of S plus gamma times the max over A of the expected utility, right? Except we have some estimate of the utility at time t, okay? And probably the right thing for me to do would be to write this like as U hat or something like that. This is my estimate of the utility. And so now using this, I'm going to want to sort of update the, all of my utilities and make them better. And it turns out I can do that by simply doing this. So I'm going to update at every iteration, update utilities based on neighbors. I'm going to update at every iteration my estimate of the utility of some state S by simply recalculating it to be the actual reward that I get for entering state S plus the discounted utility that I expect given the original estimates of my utility. Does that make any sense at all?
Yeah, I guess so. So the S, okay, so we need the whole U hat T, like at all states, because we're not just using the values at state S to update the values at state S. We're using all the values at the previous time step to update all the values at the current time step.
Yep.
So all these n equations are all tangled together.
Right, because of this expectation. So really, just to make it clear, this should be a summation over S prime. So I'm going to update the utility of S by looking at the utilities of all the other states, including itself, S prime, and weight those based on my probability of getting there, given that I took an action. And what action am I going to take? Well, I'm going to take the one that maximizes my expected utility.
So it's sort of like figuring out what to do in a state, assuming that this U hat really is the right answer for the future.
Right. Now, why is that going to work? So I just made up the U hats, right? They started out as arbitrary utilities. The next little step about updating utilities based on neighbors makes some sense because effectively a neighbor is any state that you can reach, which is determined by the transition function. But all I'm doing is reaching states that are also made up of arbitrary utilities, so arbitrary values. Why should that help me? Well, it's because of this value right here. This is actual truth. The actual reward that I get for entering into a state is a true value. So effectively what's going to happen is I'm going to be propagating out the true value or true reward, the true immediate reward that I get for entering into a state, say, through all of the states that I'm going to see and propagating that information back and forth until ultimately I converge.
It's still not obvious why we should converge because we start off with an arbitrary function and it seems like that could be really wrong. So we're like adding truth to wrong.
Yes, but then the next time around I've been adding truth twice to wrong. And then more truth to wrong and more truth to wrong. And eventually I'm going to be adding more and 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 more truth, and it will overwhelm the original wrong.
And does it help that the wrong is being discounted?
Yes, it helps that the wrong is being discounted. Does it help that the wrong is being discounted? I actually don't know that matters. I have to think about that for a moment. It certainly doesn't hurt. But I guess the way that I think about this, I mean, there's an actual proof. You can look it up. But in the end, I tend to think of this as a kind of simple contraction proof that effectively at every step, you have to be moving towards the answer because you've added in more of the reality, more of the truth. And if you remember, the utility of a state is just all the rewards that you're going to see. So basically at every time step, you've added the reward that you're going to see and then all the rewards you're going to see after that. And so you've gotten a better estimate of actually the sequence of rewards you're likely to see from a state. And if that gets better for any of the states, then eventually that betterness will propagate out to all the other states that they can reach or they can reach them. And that'll just keep happening and you'll keep getting closer and closer and closer for the true utility of the states until eventually you run out of closeness.
Cool.
Does that make sense at all?
Well, so does it also help that the gamma is less than 1?
Yeah, it does. The way I like to think of this is as a sort of contraction proof. If you've heard of those. So the basic idea here is that you start out with some noise, but at every step you're getting some truth, and that truth gets added, and then the next iteration, more truth gets added, and more truth gets added. So as you have some estimate of some particular state S, you get to update it based on truth, its actual reward, and you bring in more truth from the other utilities as well. As this particular utility gets better, that closeness to the true utility then gets spread to all the states that can reach it. And because the gamma is less than 1, you basically get to overwhelm the past in this case, which is the original arbitrary utilities. And so as you keep iterating through this, the latest truth becomes more important than the past less truth. And so you're always getting closer and closer and closer to the truth until eventually you do. At least that's the intuition that I like to think of.
Yeah, I kind of get that as an intuition, though I'd probably be happier going through the math. But
well, we could do that. And by we, I mean the students can do that by actually reading the proof.
all right.
Okay, so cool. So this right here is an easy way to find the true value of states. And you do it by iterating. And it kind of has a name.
It kind of has a name.
Yeah, what do you think the name might be?
Bellman's algorithm.
No, though that's probably reasonable.
Utility iteration.
Yes, except utility sounds better if you say value. So it's value iteration. And it works remarkably well.
So, and it doesn't give you the answer, but it gets you something that's closer and closer to the answer.
Right, and eventually it'll converge or get so close to converging it doesn't matter. And once you have the true utilities, if you recall, we know how to define the optimal policy in terms of the utilities. So if I give you the utilities, then the optimal policy is just, well, I'm in a state, look at all the states I might get to, figure out the expectation that I'm going to get for a given action, pick whichever one is maximal, and I'm done. So solving for the utilities or the true value of a state is effectively the same thing as solving for the optimal policy. Excellent.
That's cool.
I think so. Okay, Michael, so you seem like you knew what you were doing, so I thought I would verify that by giving you a very easy quiz.
This doesn't look so easy.
It is easy. So here's the quiz. To help you, I've written up both the Bellman's equation and the update that we would give to utilities. I've neglected to write the little hats and everything because I just don't think you need that. But these are the two equations that you need to be able to think about. This is just what we've written up before. And I've written down the grid world we've been playing with the entire time. And I want you to figure out how value iteration would work from the first iteration and the second iteration for this particular state here that I've marked with an X. Okay?
Okay.
All right. And there's a little more information you need to go. Gamma in this case is going to be equal to 1/2. Mainly because it's easy to do the math if you do it that way. The rewards, just to remind you, for all of the states except for the two goal or absorbing states is going to be minus 0.04. And my initial arbitrary utilities for all of the states is going to be 0, except in the two absorbing states where I already know the utilities are 1 and -1 respectively. Okay?
Okay.
You got all that?
I think so.
You sure?
I feel confident that I'm going to slip up. But, okay. Yeah, I think I can take a stab at this.
All right. So gamma's 1/2. Rewards are minus 0.04. Arbitrary starting utilities at time 0 is 0, except here at the absorbing states. Tell me how the utility here will evolve after 1 step or 1 iteration and 2 steps or 2 iterations. Okay, then. Go. All right, Michael. What's the answer?
I think I've already made a mistake.
Okay. What's the mistake?
Suggesting that we do a quiz.
I'm pretty sure that's always true. Unless, Michael, by doing a quiz now and suffering pain, you in the future are a better person, in which case you have made the right long-term decision.
I see. This is an MDP meta point you're making.
Mm-hmm.
All right. So let's just buckle down and do this thing. So
Okay.
All right. So at that state X, we have to consider, according to the equation, we're going to do U sub 1 at X. And that's going to be the reward at X, which is minus 0.04, plus gamma, which is 1/2.
Yes.
Feel free to write these things down.
Okay, so let's see. It's going to be minus 0.04 plus 1/2 times.
All right. So now we need to do 4 different actions.
Right.
So I would make like a bracey thing at this point.
Mm-hmm.
Not a bracket, but a brace. All right.
Oh. Or I could do a bracket because you're going to notice immediately that it's obvious what the right action is.
Okay, all right. Well, we know that the right action is going to be to go to the right.
Yeah, but even then, you don't have to do the rest of the computation because my first guess at all the utilities is that there's 0, which means you're always going to want to take the action that gets you to +1 with the highest chance.
Right.
So there's just
I
no
see.
point in.
Okay, fair enough. Thank you
Okay.
for the shortcut. So we only have to do the one action, which is to the right. And so if we go to the right, there's 3 possible next states we could go in.
Yep.
One is back to x, which has a value of 0.
Mm-hmm.
One is to the thing underneath of x, which has a value of 0. And then the last one with probability 0.8 is to go to the +1.
Which is
0.8 times +1.
which is 0.8.
0.8.
Okay, and that is
Okay, so 0.8 times a half is 0.4 minus 0.04 is 0.36.
yep, and that is correct.
Okay, so to do the same thing for U2, we're going to need the U1 values for a bunch of other states, it seems to me.
Maybe. So let's write that down. So we know that for now the utility here is 0.36, right?
Yeah.
And you're saying that in order to do U2, I'm now going to have to, I was able to avoid doing some of the math before because these are all zeros, and so it was just easy to do. But when I went right, I either stayed where I was, went to the +1, or I ended up going down. Well, I think by the same argument that allowed us to cheat our way out of before,
Okay.
it's still going to be best to go to the right. So
Yeah, but I know that, but the value itself is going to depend on the value in several other states.
Yeah, well, how many other states?
Oh, just that one.
Just this one. So what was U1 of this state?
I see. So presumably we want to avoid falling into the pit. So the best thing we can do is bash our head against the wall, which would get us a minus 0.04 for that state.
Right.
Okay, all right, so maybe this isn't so bad. So now for our U2 values, we need minus 0.04 plus a half times 0.1 times 0.36 plus 0.1 times negative 0.04, so that's minus 0.004, plus 0.8 times 1, which is 0.8 again, just like it was last time.
Yep.
And I get 0.376.
Which is what I get by also getting out your calculator. Okay, so 0.376, and you can imagine how we would do that on and on. I want to point something out, Michael, which is that you decided to figure out what the true utility was for the state under X by bashing your head into the wall. But you know that, based on the discussion we had earlier, that actually the optimal policy would involve going up instead of bashing your head into the wall. But what you did at that point was in fact right, because everything else, the initial utilities were all 0. The best thing you could do is avoid ever falling into -1. So the policy in the very first of bashing your head into the wall is in fact the right thing to do at that point. But what you'll notice is that the next time around, the utility for the X state is bigger than 0. In fact, we'll keep getting bigger and bigger than 0. As you can see, it went from 0.36 to 0.376, which means at some point it's going to be worthwhile to try to go up instead of bashing your head into the wall.
I see. So this is kind of cool that it works, but it does seem like a really roundabout way of getting there. I mean, is there some way that we could maybe take advantage of the fact that there's not that many policies?
Yeah, so you actually said something fairly subtle there, so let's see if we can unpack it. So let me point out 2 things, which I think will get us to what you're answering. The first is, do realize that the reason that the value iteration works is because eventually value propagates out from its neighbors, right? The first time we could calculate the 0.36 without really worrying about anything around it because the utilities are all 0. And in fact, based on the initial utilities, even for this state here, we do the wrong thing. But after some time, this state becomes a truer representation of its utility, and in fact gets higher and higher. The right thing to do here will go up. You'll also notice that after another time step, I'm going to need to start looking at the value of this state as well, right? So eventually I'm going to have to figure out the utilities or the values of all of these states, and this +1 is going to propagate out towards the other states, where this -1 will propagate out less because you're going to try to avoid falling in there. So that makes sense, right? But what's propagating out, Michael? What's propagating out is the true utilities, the true values of these states. But what's a policy? A policy is a function from what to what?
States to actions.
Right. A policy is a mapping from state to action. It is not a mapping from states to utilities.
No, that's what U is.
That's
Or
what U is.
are.
So, so if we have U, we can figure out pi, but U is actually much more information than we need to figure out pi. If we have a U that is not the correct utility, but say has the ordering of the actions correct, then we're actually doing pretty well, right? It doesn't matter whether we have the wrong utilities.
I see. Uh-huh.
You'll remember we did this in the first third of the class as well when we noticed that we were computing in the Bayesian learning case actual probabilities, but we don't really care about actual probabilities. We just care that the labels are right. There's a very similar argument here. We don't care about having the correct utilities, even though by having the correct utilities, we have the right policy. All we actually care about is getting the right policy, and order matters there rather than absolute value. Does that make sense?
Yeah, that's interesting. It's almost kind of like pi is more of like a classifier, right? It's mapping inputs to discrete classes, and the U's are kind of like more like regression, where it's mapping these states to continuous values.
Right, and given the utilities, we can find pi. Given pi, there's an infinite number of utilities that are consistent with it. So what you end up wanting to do is get a utility that's good enough to get you to your pi, which is one reason why you don't have to worry about getting the absolute convergence in value iteration. But it gives us a hint of something we might do that's a little bit better with the policies that might go faster in practice. So I'm just going to take 3 seconds to give you an example of that, okay?
Awesome.
Okay. Okay, so Michael, let's see if we can do something that might be faster and just as good as what we've been doing with value iterations. And what we're going to do is we're going to emphasize the fact that we care about policies and not values. Now, it's true that given the true utilities, we can find a policy, but maybe we don't have to find the true utilities in order to find the optimal policy. So here's a little sketch of an algorithm, okay? So it's going to look a lot like value iteration. We are going to start with some initial policy. Let's call it pi sub 0. And that's just going to be a guess. So it's just going to be an arbitrary setting of actions that you should take in different states. Then we're going to evaluate how good that policy is. And the way we're going to evaluate it at time t is to calculate its utility, which I'm going to call u sub t, which is equal to the utility you get by following that policy, okay? And I'll show you in a moment exactly how you do that, all right?
Okay.
But I just want to make certain that you kind of buy that maybe we could do that. So we have, given a policy, we ought to be able to evaluate it by figuring out what the utility of that policy is. And again, we'll talk about that in a second. And then after we know what the utility of that policy is, we're actually going to improve that policy in a way similar to what we did with value iteration. We're going to update our policy time t plus 1 to be the policy that takes the actions that maximizes the expected utility based on what we just calculated for pi sub t. Now, notice that will allow us to change pi over time, because imagine that we discover in some state that actually there's an action that's very good in that state that gets you someplace really nice, gives you a really big reward, and then that point on you do fairly well. Well, then all other states that can reach that state might end up taking a different action than they did before, because now the best action would be to move towards that state. So these two steps will actually, or can actually, lead to some improvement of the policy over time. But the key thing here is we have to figure out exactly how to compute u sub t. Well, the good news is we know how to do that, and it's actually pretty easy, and it boils down to our favorite equation, Bellman's equation. So our utility at time t, that is the utility that we get by following the policy at time t, is just, well, the true reward that we're going to get by entering that state plus gamma times the expected utility, which now looks like this. There, does that make sense? Do you see that?
Okay, wait, hang on. It looks a little different from the other equation. So did you mean for it to have t, ut is defined in terms of ut and not ut minus 1?
Yes.
Okay, that's interesting. And the max is gone, but instead of a max, there's a policy stuck into the transition function, right?
Yep.
The choice of action is determined by the policy.
Right. And that's actually the only difference between what we were doing before, is that rather than having this max over actions, we already know what action we're going to take. It's determined by the policy we're currently following.
Okay, but isn't this just as hard as solving the thing with the max, you said?
Well, what was the problem that we were solving before with the max?
That was the Bellman equation.
Yes, but we were solving a bunch of equations. How many of them?
N.
So we were solving n equations and how many unknowns?
N.
What's the difference between this n equations and n unknowns and the other n equations and n unknowns?
Well, N is the same.
Mm-hmm.
There's no max, though.
There's no max. And what was it that made solving that hard before?
The max made it nonlinear. The max is gone now. Are you saying this is a set of linear equations?
Yeah, because, well, it's just a bunch of sums. And the pi is not like some weird function. This is just effectively a constant.
I see.
So now I have n equations and n unknowns, but it's in linear equations. And now that I have n linear equations and n unknowns, I can actually compute this in a reasonable amount of time by doing matrix inversions and regression and other magic hand-wavy things.
That's very slick. It seems it's still more expensive than doing the value iteration update, I guess.
Yeah, but you don't have to perhaps do as many iterations as you were doing before. So once you've evaluated it, which we now know how to do, and you've improved it, you just keep doing that until your policy doesn't change.
Very cool.
Mm-hmm. And this does look a lot like value iteration to you, doesn't it?
Yeah, though it seems like it's making bigger jumps somehow.
It is, and that's because instead of making jumps in value space, it's making jumps in policy space, which is why we call this class of algorithms policy iteration.
Cool.
Right. Now, this inversion can still be fairly painful. It's, if we don't worry about being highly efficient, it's roughly n cubed. And if there are a lot of states, this can be kind of painful. But it turns out there's little tricks you can do, like do a little step of value iteration here for a while to get an estimate, and then, kind of cycle through. So there's all kinds of clever things you might want to do, but at a high level, without worrying about, the details of constants, this general process of moving through policy space and taking advantage of the fact that by picking a specific policy, you're able to turn your nonlinear equations into linear equations, turns out to often to be very helpful.
So is it guaranteed to converge?
Yes.
Nice.
Well, that was easy. I'm not going to go into it, but there's a finite number of policies. You're always getting better, so eventually you have to converge. It's very similar to or at least intuitively, it's very similar to the argument you might make for k-means.
Cool.
Okay, Michael, so this is it. Why don't you help me remember what we learned in this one marathon session that was not all distributed over multiple months?
Sure, or years. So MDP, so we talked about Markov decision processes, and we said what that meant.
Okay, so that's the first thing we did is we talked about MDPs.
And that an MDP consists of states and rewards and actions and like that, transitions, discounts.
So you said discounts, and I just want to point out that there are some people who think that that's a part of the definition of the problem, and there are some people who think that that's more of a parameter to your algorithm.
Ah, okay. All right. So there's some people who think of it the right way.
Like me, and some people think of it the wrong way. So I tend to think of the discount as being something that you're allowed to fiddle with, as opposed to it being a fundamental part of the MDP.
Well, then why not fiddle with the rewards?
Sure, you actually are allowed to fiddle with the rewards.
Oh,
but this is
you're
supposed to be
very
yes,
open-minded.
I am open-minded. I believe very much that rewards should be able to marry other rewards. In any case, the important thing here is that there's some underlying process that you care about that's supposed to represent the world. States, rewards, actions, and transitions capture that fairly well. Discount is in some sense an important part of the problem because it tells you how much you want to care about the future versus the past, but it's reasonable to think of that as something that you might want to change outside of the kind of underlying physics of the world.
I see. Okay, well, that's fair. Yeah, in some sense, the states and the actions and the transitions represent the physical world, and the rewards and the discount represent the kind of task description.
Right, and of course, you say that, but if you could decide to define states differently, and doing that would impact both your actions and the transition function and so on and so forth. But the basic idea is right, which is there's some underlying process we're trying to capture, and I think it's exactly right to say states, actions, and transitions sort of capture that, and rewards and discounts capture more about the nature of the task you're trying to do in that underlying world.
Okay, and in that context, we talked about two really important concepts, policies and value functions.
Which we sometimes call utilities.
Right.
And how do utilities differ from rewards?
The utilities factor in the long-term aspects, and the rewards are just telling you the moment-to-moment.
Right.
Utilities are like a group of rewards, like a
Yes.
gaggle
Or a murder.
of crows.
A murder of
So
rewards.
that we talked about how we can assign value to an infinite sequence of rewards,
Mm-hmm.
but it helps if we use discounting to do that so that we don't get infinitely large sums.
And that allowed us to deal with infinite sequences, but treat them as if their value is, in fact, finite. Thus solving the immortality problem.
And let's see, then we kind of, and the stationarity was a really important part of that.
Yep. In fact, kind of drove everything.
Yeah. And all these things were tied up together in the Bellman equation itself.
Yes, which is an awesome equation and deserves capital letters. Is that it?
And then we solved the Bellman equation using value iteration and policy iteration. I think
Yes.
that was it. All right, so are any of these polynomial time algorithms?
Well, the way we've been talking about them, no, but you can map these into linear programs and turn them into polynomial problems or polynomial time algorithms. So yes, these problems can be solved that way. But actually, that reminds me of something that we haven't said and that we haven't learned today that I think is worth mentioning, which is we've been talking about, this section of the class is about, or the course is about reinforcement learning. But we actually haven't done any reinforcement learning here because we know everything. We know the states, we know the rewards, we know the actions, we know the transitions, we have some discount. We have been solving MDPs, but that's not quite the same thing as doing reinforcement learning. However, it's very important to do these things to make it easier to think about how reinforcement learning works. So in reinforcement learning, the difference is you don't necessarily know the rewards and the transitions, or even the states and the actions for that matter.
I see. So, okay, so when are we going to get into reinforcement learning then?
Next time. And when I say we next time, I mean you next time. That's your assignment. Learn all
Okay.
about reinforcement learning and talk about it next time.
All right, I got to go and get to work then.
Okay. Well, you have a good one, Michael.
Thanks for all this. This is really cool.
It is cool. Bye.
Bye.
Bye.